So now let's try to interpret this and try to answer some of the simple questions and not get too deep because there's a lot to unfold here. Okay? There's a lot to unfold, and that's really what we want to be able to do. Okay, so here we go. So the first thing that I would look at is that how is mechanical energy used? I would say that typically the total mechanical energy is useless. In other words, when I look at the mechanical energy, even though it's a constant, we typically are not interested in this quantity. The power of using mechanical energy is tracking how energy changes / transforms into other types of energy. So in essence, it's an extremely useful bookkeeping system to track energy. And I would say that this by far is the most important thing about conservation of energy. And you'll see in a minute when we start looking at bar diagrams. Another thing that I should probably say here, why is mechanical energy so important? Well, there's a lot of answers to this. I would say that it's probably the most fundamental law of nature. And that means that regardless of the energy scale, mechanical energy, maybe I should not say mechanical energy, I should say total energy is a principle that holds at all scales. So that's a really important thing. That even though there's a new law that may come up in physics or in science, conservation of total energy is always, it holds at all scales, no matter what. And when you look at interactions here, And I would then say that 3, in every interaction, just like momentum 2, we only measure the endpoints of a process. In other words, if I have a before, which typically means that's our initial energy state, then this energy of before is what we measure. Then what we end up happening, and then we have a process. This is during the process, or maybe I should say the interaction. And then afterwards, we then have the after, which is our final energy state, which then tells us that we're here. So when I look at this thing, this right here we usually cannot measure details about this. So the only thing we care about is what happens before and what happens afterwards. And so what we're really looking at is we're talking about how energy flows in, into, or out of a system. And we've done this before here where we have a system here and we say that, okay, this is our initial system. And if we know that there is no external work here, then what we're finding here is that this system then is then going to stay the same. That the energy states are all going to be the same here. So even though I have a flow of energy coming in, and I have a flow of energy going out, that system stays in an equilibrium state. It's in an energy equilibrium state, right? We call this an energy equilibrium state because the energy initially has to be the same as the energy afterwards. You can't destroy or create energy. You can only transform this process here. So picture-wise, we use a bar diagram. And we say here, so from a bar diagram, we then say that we have this amount of total mechanical energy. And when we look at this, we cannot change the total amount of energy here. This has to be, this has to remain. If there's no external workings, this guy has to be a constant. So another, what this is really telling us here is that this really tells us that one cannot create or destroy energy. Is that the only thing you can do here is that you can transform energy. And so now I have a system. Maybe in this system, I have this much of spring potential energy at 7.1. Maybe I have this amount of energy in gravitational, and then maybe the rest of this becomes all kinetic energy at this spot. So then the only thing we track with conservation of mechanical energy is how are these things changing? Maybe what happens here is that we have a situation where now the spring energy at state 2 increases in such a way that it all becomes, most of it becomes that, but the fact is that it has to stay the same. And if I keep doing the opposite, maybe now all of a sudden here, the kinetic energy at 3 is 0. And then all of a sudden, the system starts to change where now I have some spring potential at 3, and the rest of it then has to be gravitational potential energy at this point. So when you're looking at this, the only thing we care about is that how is it transforming? So this is what I mean by the bookkeeping system. How are the individual energies transforming, and therefore the bar diagram tracks / a bookkeeping system as how energy behaves. And this becomes important. Why is this so important? Because now the size of the bar diagram gives us information. So the size of the bars tell us lots of physics. For example, what if I have a little tiny bar for kinetic energy right now versus a bar that's large? What we're seeing here is that this guy, if I look at this little tiny bar tells us what? Well, if it's really small, it's going to tell us that this is a slow speed compared to this guy being a fast speed. So by using the bar diagram, we could talk about how fast an object is moving. But I could say the same thing with gravitational potential energy. So if I have a little tiny bar for gravitational potential energy, and I compare this to a big bar for gravitational potential energy, then what it's telling us about, it's going to tell us about the height. So this will be a low height. this is going to be a high height. That's why it's important to track what is going on. And we could say the same thing with the spring. If I have a tiny little spring for my bar versus a large bar, then it tells us about the compressions here. So what this tells us in this case is that you have little compression. And you know what? I should also say, or little stretching. On this hand, in this way, we have a lot of compression / stretching. That's why it's so important to keep track of these energies here. And one of the things that you may not have realized here, what did I call that? 3. I should probably say it in the same way, is that individual energies are inversely proportional. Is that right? I'm not sure if I should say it like this. So what I mean by this, if I know that the mechanical energy is a constant, then what this tells me here, if I have this amount of kinetic energy, and then let's say that I have that amount of potential energy. So when I just write the U like this, I'm talking about gravitational as well as spring. So what this means here is that if somehow the kinetic energy decreases, the potential energy has to get larger. On the other hand, if the kinetic energy gets large, you have no choice but to conclude that the potential energy gets smaller. So this ratio of each other really makes a big difference as to what is going on here.